Can you all hear me? Oh, hopefully. Yes, okay. I'm gonna give it 2 minutes because it's not 1:30 yet. All right, that's good. Thank you. Hi. So just like last time, thank you, Michelle. Just like last time, I'm going to be assuming you guys have done the worksheets already, and I'm just gonna go over them one by one. If you have any questions, you can stop me by just saying something in chat or saying something on your microphone, whatever works. Thank you again. You don't necessarily have to say present, like as long as you say something in chat, that's good enough for me, just so I can see who was here. But thank you anyway. Okay, I'm just gonna give it like another minute or two to see if more people will show up before I start going over stuff, because there's only 5 of you. I'll write the things for the first question, at least. Okay. Okay, I see some more people came. As you join, I'd appreciate it if you just said something like hi or present so you know you were here. But anyway, I'm gonna get started. So here's the first problem on worksheet 14. The chiral center is right here. Thank you, Natalie. So we have to rank the substituents on this chiral center to be able to determine if it's RS. And there is a hydrogen that I didn't draw in, but it's on the dash. That gets number 4 because it has the lowest atomic number. And then there are carbons attached to the chiral center. And if you compare carbon to oxygen, oxygen has a higher atomic number, so it gets priority number 1. And then what is next is looking at what's attached to these 2 carbons. So attached to this carbon is an oxygen, whereas this carbon is attached to another carbon. So because of that, this side gets a higher priority because the oxygen over here is closer to the chiral center than the oxygen over here. Even though that's a double bond, it depends on where it is in relation to the chiral center. So you have to be a little careful. That was sort of the curveball I had here. So it's 1 for the hydroxyl, 2 for the side with the ether, and then 3 with the aldehyde. And the arrow goes like this. It's going counterclockwise, and the hydrogen's in the back, so this is S. And this is review. It's something we've done a lot, so hopefully you guys are good with it, but it's good practice. Thank you. Okay, so for the second one, the methyl group's gonna get number 4 because everything has a carbon, but the methyl is just one carbon by itself, so that just has like the shortest chain. That's an easy way to figure that out. And then if we look at this carbon here, the double bond is like a double bond is equivalent to a carbon being bonded to two carbons like this. So based on that, like this carbon here is bonded to two other carbons. Well, this carbon is only bonded to one carbon. So that makes the ethyl group get a lower priority than the alkene. The alkene gets number 1, and then the rest of the cycloalkene gets number 2, and the ethyl gets number 3. This is a bit of a mean problem. I don't think he put it on the test because it's just a bunch of carbons, but it's not too terrible, I think. But this is the ranking regardless. And this is how you draw the arrow. It's going counterclockwise, but the methyl group here is on a wedge. Number 4 is in the front, so it looks like it's S, but you have to flip it. So it's R. Hopefully there aren't any questions. I'm going to erase the board. You can take a screenshot or look at a recording if I post that later. I'm gonna skip number 2 because I made this worksheet before I knew you guys didn't have to do HDIs, so don't worry about that. That won't be on your test. Number 3 though. Here is the first substrate. Okay, so there's 2 spots that I tried to make look like they were chiral centers. Here and here with the dashes and wedges. But there's a methyl group at the end of the chain there, and then a methyl group here. It's the same substituent, so this isn't a chiral center. And then at this spot, there are 2 hydrogens, because every carbon has to have 4 bonds. It was only bonded to a carbon and an oxygen. It needed 2 other things that I just didn't show you. These 2 are the same. That's not a chiral center. So this was a chiral. There weren't any chiral centers in this molecule. And here, that's sp2, and something has to be sp3 hybridized to potentially be chiral. So again, if there's no questions, I'll move on. Okay. The second part's number 3. And this is equivalent to, I'm not gonna put the substituents, but I'll abbreviate it. Should be able to like differentiate these 2, or like they're the same thing. So the stuff on the sides is facing towards the front, so this stuff is in the front, and then this stuff is in the back. Okay. So here, this. So this carbon at the top is bonded to a methyl group, a chlorine, a hydrogen, and then the rest of the molecule. That's 4 different substituents. So this is chiral, and that's the same case with the other carbon bonded to a chlorine. So that is also chiral. And this might look like a meso compound, but it's not meso because it doesn't have an internal mirror plane. If it did, it would look like this, because like now the 2 chlorines, if you reflected the molecule, you'd see that the chlorines just go into each other. But here, if you did the reflection, the hydrogen like this would go here, and then you wouldn't have the same molecule, so there's no internal symmetry. So this isn't what we have. That's just what it would be if it was meso, but this is chiral. And if it was meso, it would also be achiral, but again, that's not what we have. So there's that. Hopefully the fact that you guys don't have questions means you guys are good with this, because we've done it a lot over the semester. Again, if you have questions, feel free to ask. Okay, so all of these things that look like they're chiral are chiral. There's hydrogens that I didn't draw on, but those are different from everything else that's bonded to them. There's an oxygen here and a carbon here, those are different, and then we can differentiate this side of the molecule from this side with this carbon here. And then like it's the same case everywhere else. We can differentiate the two sides of the cycloalkane. So there's two different substituents. And there's no mirror plane here, so it's just a chiral molecule. Pretty straightforward. Okay. On to number 4. So if we added a proton to this, it would just be like the first step in that reaction where you add HCl or HBr or water with an acid catalyst, which you guys went over today, I think. It's just adding the proton, but then you have the cation and nothing else. So we're just looking at the different cations that can form as intermediates, basically. For this, there are 4 potential cations that can form because we have 2 double bonds, and at each double bonds, 2 different cations can form. So I'm just gonna draw them out. This is one of them. If the proton added to the alkene on the left and the hydrogen was put here, and then we'd have the double bond here still. We could also get the proton down here, and the hydrogen was added up here. It's gonna get a bit crunched for space, probably. So now we're looking at the other double bond. Oh, and if that happens, the hydrogen would have added here. Right. Okay. So in terms of like ranking stability, you should know that the more substituents the cation has, the more stable it is, because the different alkyl groups, like let's say we're looking at this one, it has free carbons attached to it, and all those carbons are going to give it some of their electron density to stabilize that positive charge. So the more substituents it has, the more stable it is, or like this is tertiary because it's attached to free carbons. This is primary, this is secondary, and this is tertiary. So like tertiary is more stable than secondary, which is more stable than primary. And I didn't really mean to do this, but I mean, when I designed this problem, that both of these are tertiary, so they're both equally stable, and they're the most stable. So that's the answer to this. They're both equally stable because they're both tertiary. And then the secondary one would be the second most stable, and this would be the least stable, the primary cation. Any questions about this? No. Okay. Moving on to number 5. It's naming molecules. When I say a complete name, that means indicating like stereochemistry, so R, S, sister trans, E or Z, all that stuff. So for this first one, before you want to get into like stereochemistry, you should probably figure out like what the base name is minus stereochemistry. So there is a 6 carbon long chain, so it's going to be hexene, and it's going to be, well, I should have numbered it before I did that, but it's going to be 2 because you want to start numbering from the side closest to the double bond, which is the left side, so that gives carbon number 2 being the beginning of the double bond. And then there's a methyl group at free, so it's free methyl 2-hexene. And now in terms of stereochemistry, we're looking at this double bond here. So what we can do is, I'm going to get rid of that circle. We can cut the double bond in half and look at both sides of the double bond and determine what has the higher priority using those same rules we used for RNS configurations. So on the left side, there's a methyl group and a hydrogen. The methyl group gets a higher priority, so I'm going to circle that. And then on the right side, we have a methyl group and then a propyl group. That's what the free carbons are here. So the propyl has more carbons, so it gets a higher priority. So on the left side, the higher priority group is pointing, not bottom, I'm gonna say down. The higher priority group is pointing down, and then on the right side, the higher priority group is pointing up. They're pointing in opposite directions. So they're trans or E. So I didn't leave myself enough space, but you put like an E in parentheses and then the rest of the name to indicate this. And if there were multiple double bonds with stereochemistry, you'd want to put like, you'd put 2E for this one, and then, okay, so like if I had another double bond, I'm just going to draw something random like this. Then I might put like 2E and then 4E or something along those lines. But if there's only one, you don't have to specify where it is. If there's no questions, I'll move on. Do the top right part of number 5 now. That's a bromine, just kind of poorly drawn, sorry. Okay, so again, we should name it like the base name before looking at stereochemistry. You might be tempted to start numbering it from this side because the methyl group is on carbon number 2 over here. But again, we give priority to the double bonds when we're naming alkenes, so we have to start numbering over here because it's closer to the double bond. So this is how you number this molecule. So we've got an ethyl group at carbon 6 here. We have a methyl group at carbon 8 and a bromo at carbon 3. So it's going to be free bromo 6 ethyl 8 methyl, and then the double bond starts at carbon number 3, so it's free, and then this is 9 carbons, so it's non-ene. Okay, and now we can look at the RNS configuration at carbon 6 because that has 4 different substituents on it. And we can also look at the E or Z configuration at the double bond at carbon 3. Those are both things you have to do if you want to give something's complete name. So looking at carbon number 6, we should rank the priority of the substituents on it. Towards the right is a double bond and a bromine, so it's kind of cheating, not really using the rules, just looking at like what's attached, because it's just a bunch of carbons everywhere else, but that's the way I approach it. I just see the double bond and the bromine relatively close, so I know that gets a higher priority. And then towards the left, we have a isobutyl group, which just, it has more carbons, and the carbons are like attached to more carbons than they are in the ethyl group, so that gets a higher priority than the ethyl group. And then there's a hydrogen on number 4, and that's on a wedge. So the arrow from 1 to 2 to 3 looks like this. It's going clockwise, but because the hydrogen is on a wedge, it looks like it's R, so this is S. So that's the R and S configuration. And then looking at the double bond, I'm again going to circle the stuff that has the higher priority on both sides. So on the right side, there's a bromine versus a carbon here. So bromine has a higher atomic number, that gets a higher priority. And then on the left side, there's a hydrogen versus a carbon and the rest of the molecule. So this gets a higher priority. Sorry, I know my drawing's crowded at this point, but hopefully you can follow what I'm doing. So on the right side, the higher priority is pointing down, and on the left side, it's also pointing down. So they're both pointing in the same direction. This is cis or C. C is technically better, but either would probably be fine. So it's C, and then S, and then free bromo, 6-ethyl, 8-methyl, free nonene. Okay, let's erase the board. If anybody has joined in the past 10 minutes, I guess, and they didn't say anything in the chat yet, I'd appreciate it if you did, just so I have a record that you were here, because I noticed some more people joined. Thank you. Okay, so again, name the skeleton, and we're going to start numbering from the left because that's the side closer to the double bond. Even though it gives the substituents a larger number than we would if we started from up there, where the 7 is. So we have a methyl group at 5, and that's the only substituent. And it could have theoretically made that methyl group into a chirality center, but it didn't give that in this problem. So don't worry about chirality if you can't determine it. It's not possible to determine if this is R or S if you're not given dashes and wedges. So that's just something to keep in your mind, I suppose. So there's a methyl group at carbon 5. The double bond is at carbon 2, and it's 7 carbons long, so it's heptene. And now, because there's only carbons here, we can either look at the hydrogens, because there's hydrogens on both sides of the double bond. We can look at the hydrogens and see that the hydrogens are both pointing in the same direction. They're both pointing up, so they're cis to each other. Or we can do what I was doing before and circle the higher priority on both sides. So on the left, it's the carbon, versus on the right, it's also the carbon and the rest of the molecule. In both cases, they're pointing in the same direction. So they're cis or Z. So this is Z, that's supposed to be towards the left, but I didn't really have space. So it's C, 5-methyl, 2-heptene for this. Great. The last part to number 5. Okay. Sorry about that. Okay. Right, so if we start numbering from the left, we'd get the double bond at carbon number 4. If we started numbering from the right, we'd get it at carbon number. That's close, yeah. That's the skeleton. I was just showing that we can't start numbering from the right side because that's not as close to the double bond, even though this methyl group here would be given a lower number. That's just an important thing to keep in mind. Don't jump to conclusions based on substituents. Look at the double bond. So we start numbering from the left. Oh, 5, 6, 7, 8, 9, 10. So Franklin was right about the skeleton. It is 3,9 dimethyl, and then 4, it's 10 carbons long, so the prefix is dec, and then ene. Okay, so we have a chiral center here that we can assign R and S to, and we have a double bond that we can assign E or Z to. And this is not a chiral center because there's 2 methyl groups attached, so it would be incorrect to try to label that as RS. So just be careful. Sometimes that's a little curveball that can be thrown at you. Okay, so looking at this chiral center, this would get priority number 1 because there's a double bond attached to this carbon. So that gives it more carbons than there are over here with the ethyl group, and the ethyl group has an extra carbon compared to this methyl group. And then there's a hydrogen I'm not going to draw on. So here is the arrow. It is going counterclockwise, and the hydrogen's in the back. So this is S. And now if we're going to look at the double bond, we can again look at the hydrogens if we want. I'm just going to put the hydrogen way up here. The hydrogens are pointing in opposite directions. And if we want to look at the higher priority on both sides, there's a carbon here versus hydrogen, and there's a carbon here. Can't really see my circle, but I guess just this whole area is higher priority versus the hydrogen. So this is pointing up, and this is pointing down. They're pointing in opposite directions, so that is E or trans. So the name for this, including the stereochemistry, is E, and then the S, 3,9-dimethyl-4-decene. And if you forgot to put the E and the S, that would be technically incorrect if you're asked for the full name, so that's important to pay attention to. Okay. Now number 6 is ranking the stability of alkenes. So I'll just go ahead and draw the substrates. Hopefully without running out of room. Okay, so the stability of alkenes basically follows the same pattern as the stability of cations. So like the more substituents the alkene has, the more stable it is. So we can just look at how many substituents each alkene has. If we look at this one, it has a substituent here and a substituent here, and that's it. It has 2 substituents, so I'll just put a 2 in the chain. In the ring, I'll put 2 here. Oh, I might have made a mistake on my answer key then. Okay, well, that's my bad, but I guess we'll get to that. Okay, this also has two substituents. And then this has 1, 2, 3. And this has 4. I could have sworn I put 1 that only had 1. That's my bad. Okay, well, what I should have done is this, because this only has 1 substituent. So let's just pretend this one wasn't on the worksheet, I guess, because if it was, it would have equal stability with this one, because they both have 2 substituents, and that's a mistake I made on the answer key. So if you were confused by that looking at the key, I'm sorry. I'm prone to making mistakes too, but let's just go off of this. This has 1 substituent. Now they all have different amounts. And like I said, the more substituents they have, the more stable they are. So this is the most stable. This is the second most stable, the third, and the fourth most stable. Does that make sense? Just looking at the different alkyl chains attached to the double bonds on both sides, and you're not counting hydrogens. I don't think you'd be counting chlorines and hydroxyls either, because, well, you might actually, but that probably won't come up if he's asking about stability of alkenes, so just worry about the carbons attached to an alkene. And since no one is saying anything, I guess you guys are good, so I'll move on. Okay, so moving on to number 7. This is identifying nucleophiles and electrophiles. So we have a benzene ring, we have a nitro, and the chat box is kind of in the way, so I'm going to draw it over here. Okay, so in general, if something has a positive charge, it'll be an electrophile. And if it has a negative charge, it'll be a nucleophile. So even though, like, you don't necessarily know what these two, well, you know what benzene is, but you might not know what it'll react as, and you haven't seen nitro groups much. Like, you don't really have to know the context of the reaction. If you just know positive is electron deficient, they want electrons, so they, phile means love, and electro is like for electrons, they want electrons, so this will be the electrophile, the nitro group. And then by default, the benzene has to be the other thing, so it's going to be the nucleophile. And it can be a nucleophile because of the double bonds in the ring. The double bonds are somewhat reactive, but you'll get to that probably next semester or the end of this semester. It depends how far he gets, but you'll learn about this reaction. But this is how we determine nucleophile and electrophile here. Okay, next on number 7, 7b. That's a poorly drawn acetone. Okay, so here it might have thrown you off because of the sodium here, but sodium is a cation. It has a positive charge, and you should know that because sodium and chlorine, that's just salt. They normally form an ionic pair, and they kind of cancel their charges out. Is it a positive charge? Like, it's just a counter ion, because things in solution don't like to be stable. If that sodium wasn't here, then we just have this with a negative charge on the oxygen. So as soon as you see that negative charge, you should be able to recognize that this was a nucleophile. The sodium was just there to help stabilize the negative charge, basically. So that's a little curveball that can be thrown at you. Just recognize if you see like a sodium or a potassium or any other group 1 elements, they're generally just counter ions to stop negative charges like this, or on a nitrogen, or like a halogen or whatever, just to stabilize that. So this is an alkoxide, it's a nucleophile, and an acetone is an electrophile. And we know it can be an electrophile because of this dipole. The carbon here is partial positive. So that explains why it acts as an electrophile. Okay, no questions, good. And the last part to 7. Okay, so again, negative generally means nucleophile, so this one is kind of straightforward, identifying the nucleophile. And then this can be an electrophile, again, due to the dipole. This carbon has a partial positive charge and the chlorine has a partial negative, so the carbon wants electrons and it gets electrons like this. I didn't ask for the mechanism, but that's what happens. It's pretty straightforward as long as you recognize the dipole. Okay. Now number 8. I drew one too many carbons. Okay. Okay, so these are both 2-butene. It's just an isomer. But this is trans because this is the higher priority on the left and this is the higher priority on the right. This is pointing down. This is pointing up. They're pointing in opposite directions. So this is trans, or E. And then this is cis, or is E. And a trans isomer for alkenes is more stable than a cis isomer. So this is more stable. And that's the case because what's attached to this double bond is carbons. Carbons are very bulky because it's a carbon and it has a bond with 3 hydrogens. So they're just pretty bulky, and you can see these two, like, I mean, the drawing doesn't really show it, but they're kind of close together because they're pointing in the same direction there. And just like when we were looking at conformational isomers with like the Newman projections, like when we had something like this, these two were getting close to each other, then there was some steric hindrance. They weren't happy getting close together because they were large molecules. It's the same idea here. So steric hindrance makes it unstable, makes the cis isomer unstable, and the lack of steric hindrance in the trans isomer makes it more stable. So that's another pattern with alkene stability. You should be able to recognize the substituents, how many there are, and how that makes something stable, and then cis and trans. Okay, I'm going to erase the board now. Now number 9. Okay, so for this is kind of going over the Markovnikov rule a bit. I just didn't straight up say it. So the first step to this reaction is going to be the same for both products. We have the nucleophile and the double bond, and then the electrophile and this hydrogen. because the bromine steals electrons from it. So we take the electrons from the double bond and push it towards the hydrogen, and then we break this bond. I'm gonna go down here. So now one of the carbons in the double bond gets the hydrogen, and then the other one gets a positive charge. Here is one of the potential intermediates that could form. And then if we have the cation like this, the bromine will attack the positive charge. And we get this as a product. And then the other intermediate that can form is if the hydrogen attaches here, and we get a positive charge here. And the bromine attacks the cation again. And the bromine is now here. So these are both potentially products that could form, but this is the major product, and we almost see none of this. And that's because of that cation stability I was talking about a while ago. This intermediate is a secondary cation. Well, this is a tertiary cation. The tertiary is more stable than the secondary. So this is Markovnikov's rule, like, because the tertiary cation is more stable, it forms more quickly. So that intermediate is forming faster, and because it's forming faster, that's what this bromine will be reacting with. So it leads to this product, pretty much only that product. So you get the more substituted bromine is your product. That's Markovnikov's rule with this. And you've seen today, I think in lecture, like, you can add hydroxyls with Markovnikov's rule. You'll see some other stuff, but you should just be able to recognize when something is Markovnikov and when it's anti-Markovnikov. But this is just one example. Okay, and now number 10. Hopefully some of you have questions about this one. So here is the first part to that. I'm going to redraw its skeletal structure to make it easier to see, but this is what I gave you. It's a butane with a cation at one end of the chain. So that's just 4 carbons with a positive charge like this. This is a primary cation because it's on this carbon, which is only attached to one other carbon. So what can happen is we have a hydrogen on a neighboring carbon, and the electrons from this bond, like the hydrogen and its electrons, both move towards this carbon here where the positive charge is. So that is called a hydride shift. And it's called that because a hydride is a hydrogen with a lone pair. And that's not entirely what's happening, but like I said, we're taking the hydrogen and the electrons here and moving it. So we're basically moving a hydride. And when that happens, now this carbon here that had 2 hydrogens, it now has free, so it is neutral. And now this carbon here that had 2 hydrogens now only has 1, so it only has free bonds, and it's now positively charged. And this is a secondary cation. So we went from primary to secondary, and primary is less stable than secondary, so we formed a more stable cation. So this is something that can potentially happen. Does that make sense? I think you guys saw that in lecture, at least a little bit. And this is important to be able to recognize. If a cation can shift in a molecule like this, it probably will happen to some degree. If it can't happen, then the molecule is just stuck with what it has, but that depends on the structure. No questions? Okay, that's good, hopefully. It's moving on to 10b. I'll again draw the question as it was given to you, and then I'll draw the skeletal structure. So the positive is on this carbon here. And this is the substrate we have with the positive charge here. So this is a secondary cation, and we're not going to want to go in this direction because that would make a primary cation, and hydride shifts don't happen to make less stable cations. That wouldn't make sense. We always want to form a more stable cation. But we have a spot here where there are two methyl groups, so that's potential for tertiary. So there, like we can see here, there's a hydrogen here. There's a hydrogen here on that carbon. So again, we can take the hydrogen and its electrons and push it towards the cation. And now the hydrogen is over here and this carbon is happy. Now there's a positive charge here. That's tertiary cation. Again, tertiary has more substituents than secondary. It's more stable. So this is likely to happen. And yeah, that's B. If there are no questions, then that's good. Okay, and then part C, it's number 10. So we have this. This is a secondary cation. Again, you don't want to go in this direction, that would make it primary. But now this carbon here, it's bonded to free carbons here with the methyl groups, and then just draw the hydrogens in. And it's also bonded to this carbon here. So this carbon has 4 bonds already. There aren't any hydrogens on it. So we can't do a hydride shift. But instead of doing a hydride shift, what we can do is, it's basically the same thing as a hydride shift. We take, it doesn't matter what bond you take, but we can take like this bond here to this methyl and do basically the same thing. You take the electrons and the methyl, and like all of that shifts towards the cation. I think this is called a methyl shift, or more generally, because it might not always be a methyl group that you're moving, an alkyl shift, because like a straight chain carbon thing is called an alkane, so that's where the alk there comes from. But now we have a methyl group here on this carbon, and now it is neutral, it's not positive anymore. And we have a positive charge here, and that has free substituents. It's tertiary compared to secondary. This is more stable. So this is something that can happen. Did that one make sense? I'll take silence as a yes. Hopefully you guys aren't desperately confused. And then the next few problems, well, it's just one problem with multiple parts. I'll show you guys how you can recognize these rearrangements in a mechanism, because that is something that is likely to come up on a test. That's how you apply these cation shifts. So yeah, I am moving on to that worksheet 14.5. It's just one page with one problem, but I thought it was important to add because it's not that much, and these are kind of important questions. Okay, so you guys just learned about this mechanism today, so I can actually go over it. That is, I'm sorry, my handwriting's not the best. I can go over the mechanism, but if I'm just going to show you the major products, if we have water and we have H2SO4 and H2SO4, like it doesn't necessarily have to be sulfuric acid. It could be like H3O plus or phosphoric acid or pretty much any acid. This is just H3O plus as a general thing. It's an acid catalyst. And that's important for the mechanism. But when you have water and an acid catalyst reacting with benzene, then it also requires heat. You get the Markovnikov product with a hydroxyl group being attached. So the hydroxyl could either attach here or here, but this spot, if we were forming a cation, which I'll show in the mechanism since I definitely have time, going faster than I thought I would. But when I showed a mechanism, there's two cations that can form, and this one would be tertiary compared to this being secondary. So you form the more stable cation, and then that's where water attaches. Okay, so I'm gonna go over the mechanism for this one because that's something you need to know. I'll probably also have a question on it on my next worksheet, but since I have time right now, I'm gonna do that. So this is the same substrate and same reaction. I'm just gonna redraw it because I used up a lot of the slide there. Oh, I think that was fine. Whatever, okay. So step one is like, I'll just draw, I'll put H2SO4 and that equals H3O plus. So we have the double bond and we have, I'll do it the same way he did. H3O plus can also be shown like this to make it easier to sort of see what's going on. Actually, yeah. So this is similar to like the double bond attacking a hydrogen in like HBr or HCl. It's the same kind of idea. So this is what happens. It gets a proton from the acid catalyst, and then it goes to the intermediate. This tertiary cation forms because that's more stable than the secondary one, like I was saying. And then I should have put the acid catalyst on the bottom, but there's also water present. So this is the step where the water comes in. We have water, it has two lone pairs, so it uses one of those lone pairs to attack cation. And now water is attached to the alkyl chain, and it has a positive charge because it was neutral, but it formed another bond. So now it has free bonds and only one lone pair, so its formal charge would be +1. Calculated that. It doesn't want to stay positive. So now this water up here that formed in the first step when one of the hydrogens was lost, now it comes in with its lone pairs and it gives an electron to the hydrogen to get the hydrogen, and then the bond between the oxygen and that hydrogen, like the electrons go to the oxygen. And we just get the alcohol, the neutral alcohol, and then we get the acid regenerated. And this would be the same if you were just drawing H2SO4 or any other acid, it would regenerate at the ends. That's why it's a catalyst, because you might recall from Gen Chem, the catalysts are regenerated and the reactions they use, they don't get consumed. So it just kind of keeps going over and over. And then you get the alcohol attached to more substituted carbon. So that's the mechanism for this. That's something you should know, but it's very similar to the HBr reaction, like I kind of hinted towards. So it's nothing too new. I'm going to erase this now. Okay. Now the second part to that problem. Okay, so again, the first step, this double bond will give its electrons to the hydrogen, like so. And that is going to lead to an intermediate. Okay, so that intermediate will have a cation. It could either form here or at this spot, because both of those are secondary, and both of the spots on this alkene were secondary, so there's a potential for either cation forming. And when this cation forms, hopefully you guys can recognize that this is secondary, but if we look at this spot here right next to it, there is a hydrogen here, and what can happen is a hydride shift towards that cation. So now there's a hydrogen here, this carbon is neutral. Now this has a positive charge and it's tertiary, so it went from secondary to tertiary. It became more stable, so that's something that can definitely happen in the middle of the mechanism. And then once we have the positive charge there, the bromine can come in and attack. It will also attack this because that is a pretty stable product that forms pretty quickly. And I'll just draw it down here. If the positive charge were here, it could also attack there. So I'm gonna move the shot. So basically, like, there's free potential products that could form. And I feel like if this was done in a lab, you'd see a mixture of all three. You'd probably get these first two I'm drawing in abundance because I don't think methyl hydride shifts would happen that quickly, but they do happen. So you'd still see some of this. Come on. Some of this form. Oh, that's the very top of the whiteboard, but that is just the bromine. So yeah, that's hydride shift in action. I'm still not seeing questions, so hopefully this is clear to you guys. I'll move on to the next one. Part C. So again, double bond, attacking hydrogen. Could get a cation here, or we could get a cation down here. If we got that, the chlorine would come in and attack that. That would be fine. It would just go to its product. But if we get the one I drew more towards the top, this is a secondary cation. There's no, like, it's not going to want to go in this direction because that'll just form the substrate below it. That's secondary. That's not going to happen. A hydride shift won't happen, like, to make a secondary cation become a secondary cation. That's not more stable. That doesn't happen because it would probably take energy for the hydride to shift. So it always wants to form a more stable cation. But towards the top, there's those two methyl groups. There's no hydrogens to shift, but we can shift one of the methyl groups like this. And when that happens, we have the methyl group moved, and there's a positive charge here. And that is a tertiary cation that's more stable, so that can happen. So now, like the chlorine, I wouldn't recommend, if you were asked to draw a mechanism, to do it like this with both arrows at the same time, but hopefully you guys recognize that I'm just trying to save time by not just drawing that again just to show the chlorine attacking. But the chlorine attacks the cations, and that leads to a mixture of products. So you get the two things from no methyl shift, just those two cations. And then you'd also get the one where the methyl shifted. And those are all the products that you would probably see. So that's that. Still no questions, okay. Then part, I guess I don't have parts, but the last one. Okay, so here's the reaction. Again, double bond, nucleophile attacks the hydrogen, electrophile. This is a pattern you're gonna see over and over again. This is the cation that forms. We're not going to see a cation form here because that's primary versus this being secondary. And you might be tempted to, like, you see a hydrogen here and you would do a hydride shift like this to move the cation to be over here. That's not what happens because that is too far away. A cation can only shift one carbon at a time, and like if I'm gonna number these, that's 2 carbons away. It's too far away for hydride shifts to happen. And it's not going to shift towards carbon number 2 and then towards carbon number 3, because like I said, these shifts only occur to form more stable cations. So this is secondary. If it shifted towards carbon number 2, it would still be secondary. That's not more stable, that's equally stable. So it used energy to basically just get the same result. It would have been a waste. So that doesn't happen. So all that happens here is the chlorine attacks the cation, and you get the product that you've all been expecting since you started doing these mechanisms, just this. So it's possible that he'll make it look like you could do a hydride or methyl shift, but you can't because the stuff is too far away. So just be mindful of that, is what to learn from this. That's everything I have for today. If you guys don't have any questions, you're free to leave, and in like half an hour, I'm just going to be doing this again, so definitely don't feel obligated to watch me do that. But that's all I have for today. Next Tuesday, I'll be going over mechanisms and some of the reactions you've been learning, but unless you want me to just go over the mechanisms, even though you probably just saw them today, I'm just going to be done. But I'll be here. So if you have a question, feel free to put in chat. Otherwise, yeah, you can go.